you very much for this invitation. I'm taking the advantage of this invitation to make a little advertisement of a recent paper. So continuing on the relationships between surface processes and the deep evolution of reefs, but changing a little bit the perspective towards the magmatic history of reefs rather than the structural evolution of reefs. And this is also because it seemed to me, reading the bibliography, that the potential relationship between surface processes and magmatic activity at reefs were considerably understudied with respect to the work that was done related to the relationship between surface processes and the structures. So, however, we all agree that magmatism and surface processes, they both contribute to the evolution of reefs. And if we consider the reefs are often divided into two end members cases, volcanic and magma poor reefs, we can wonder about these relationships. So for instance, if we look at volcanic rifted margins, there are often large igneous provinces, high velocity lower crustal levels, and seaward dipping reflectors, which are nearly always located in proximity of thick sedimentary basins. And in cases such as Iceland, for instance, there has been actually a number of studies investigating the relationship between surface redistribution of the masses, especially in terms of formation of and melting of the ice sheets and the production of magma and transfer of magma through the lithosphere and eventual eruption of magma. These studies shown quite nicely how the surface processes may actually be able to compress or decompress the geothermal depth, so that if some melt is already being produced, the volume, the amount of melt in general can actually be modulated by these effects. So that would be a surface processes forcing on the production of magma, but we can also envisage some effect on the transfer of magma as well. And if you consider that rocks are 3 times as higher density than ice, then it would be reasonable to expect some even more pronounced effect from erosion or sediment deposition. And if we then look at magma pool rifted margins, even in these cases, it's quite common to see thin-reefed magmatic bodies that get emplaced into the crust and likely interact with the sedimentary history of the rift basin. So I addressed this question about the relationship between surface processes and magmatism at rift in context with the numerical model that I'm trying to show here very quickly. So the model is made up of 5 different components. The first is the mechanical component, which basically is made up of the continuity equation and the momentum equation, which allow to relate the velocity field to density and the stress field within the model domain. There is a rheological component which accounts for viscoelastoplastic deformation of rocks according to established law that I won't go through into the details here. And then there is a thermal component, which is basically the solution of the energy equation, which allows to solve for the thermal history within the model domain. Then there is a 4th component, which is a partial melting component, which is very simplistically accounted for by assigning to each lithology a stability field within the pressure temperature domain. And this comes from experimental and petrologic studies giving the solidus and liquidus of some lithological materials that are implemented into the model. And then based on the amount of melts that is generated, the viscosity and the effective pressure of the material is corrected accordingly to established laws. And then the final component of the numerical model is the surface process component, which is a diffusion law. So a diffusion law is a very simplistic way of addressing surface processes, but in this context is very convenient because it allows at one go to account for erosion of the reef shoulders and filling of the sedimentary basins that forms during rifting. So according to this law, the evolution of the topography, the changes of the topography in time is given by a coefficient and the second derivative of the topography in space. As I said, this is rather simplistic. There are much more evolved physical laws to account for surface processes, but as I'm trying to figure out the very first order relationships between surface processes and magmatic activity, this seemed to be a convenient way of doing it. This is the reference model setup. Geometry and structure. So there is basically two materials within the model domain, one material for the crust and one material for the mantle. And the differentiation between lithospheric mantle and asthenosphere is defined based on the thermal structure that is pre-imposed to the model at the initial stage. And then I prescribed extensional velocities on the vertical side boundaries and a weak seed here to initiate the deformation in the middle of the lithosphere in the central part of the model domain. So I'm showing here two example numerical experiments, everything being the same, except for the coefficient in the diffusion law defining the efficiency of surface processes. So in the uppermost panel, in the uppermost simulations, which is given by these two panels, there is inefficient surface processes, and in the lower two panels, there is highly efficient surface processes. Now, the two panels show the lithology distribution here, so light bluish colors for the crust, and then mantle lithosphere in greenish colors, and purple is the asthenosphere. And this lower panel shows the occurrence of partial melting. So at this scale, and this is several hundreds of kilometers, it's really hard to find differences in the overall evolutions. But if you then in a post-processing phase, you actually show the evolution of the volume of melts through time that are produced for these two simulations. Again, purple is inefficient surface processes, and this SP coefficient is the coefficient used for the diffusion law. And you can really think of these as a characteristic rate of erosion and deposition for the simulation in millimeters a year. So that would be erosion deposition rates of 0.1 millimeters a year for the purple simulation and 10 millimeters a year for the blue simulations. And then there is this yellow-red bar here, which represents the material that is undergoing to melting. So yellow is the crust and red is the mantle. So you recognize yourself that in the first stages of extension, there is once the mantle lithosphere has been broken apart, there is the crust, which is subject to dominant partial melting. And efficient surface processes implies more melting of crustal material. And then in the later stages of the model domain, the asthenosphere is subject to partial melting. And in this case, efficient surface processes implies less melting of material. And in a few slides, we'll try to understand why this happens. But first, I'd like to show that these are the results for this specific set of conditions: extensional velocities 1 centimeters a year, mantle potential temperature 1200 degrees, and MOHO 35 kilometers. If you slightly increase the mantle potential temperature, or you increase the extensional velocity, or you increase the MOHO thickness, the crustal thickness, these trends are actually still visible, but they are very much smoothed out. So thermal anomalies, fast extension, and a thicker crust actually reduce, according to this model at least, the influence of surface processes on rift magmatism. If you then try to understand why, this is actually interesting because from the parametric study, we can isolate a set of conditions according to which surface processes may be more likely influential in the magmatic history of a rift. And this is relatively slow extension, relatively cold multipotential temperature, and a relatively thin crust. That would help a lot. So if we then look why these differences are observed, this appears when you plot the geotherm in the very center of the model domain at a given time. You recognize that the geotherm overtakes the solidus and the liquidus of the crustal material, which is represented by these black lines here. But the difference in the amount of melt is actually controlled by the position of the moho and not really by the position of the geotherm. So what happens is basically that when we are effectively filling the basins that forms during rifting with sediments, we are lowering the moho, and we are continuously providing additional crustal prone to melting material during extension. And this helps a lot in producing crustal melts. In the later stages of the model domains, what happens is somewhat different, because in this case, it's really the position of the geotherm that controls the difference in the volume of melts that is generated. And in this case, what happens is mantle decompression melting is inhibited by the filling of the sediment of the basin with sediments. So I already got to my conclusions. Surface processes seem to be able to affect the magmatic history of rifts in some conditions. And an effective way of doing it is by lowering the moho, and this especially happens if the extensional velocities are relatively slow, mantle potential temperature not higher than 1250 degrees, and crustal thickness lower than 40 kilometers, according for this particular model. And this results in a significant contribution of surface processes to partial rock melting. So given this set of conditions, surface processes seem to be more likely to affect magma production at magma pool rifted margins, especially because if a mantle plume is involved, mantle potential temperature is likely above this value. However, I'd like to point out that I'm accounting for an effect of partial melting on the viscosity and the effective density of rocks, but I'm not accounting for any effect of the presence of fluids on the sigma yielding strength, which actually decreases in the presence of fluids. So this is to say basically that I'm likely to some extent underestimating these surface processes forcing on extensional rock melting. And a possible implication of this, and this certainly requires more investigations, is that, of course, climate is the main driver of surface processes, and magmatic activity at rift margins contribute to climate changes. So there is a good potential for a nice chicken or egg problem here, which I invite everybody to investigate further, possibly with me in the future. Thank you very much. I'm happy to take your questions.
Thank you, Pietro. Do we have any questions in the meantime? Yes, John Arthur.
Hi, Pietro. I was wondering if you had a chance to look at the changes in upwelling rate, the effective upwelling rate that you could induce with changes in surface loading, and how much that would modulate the net production rate of magma, as opposed to just the magma that's present in the crust, which you're tracking.
Yeah, we had a little discussion about this by email, but I haven't gone much farther than we discussed about that. I agree. I think it would be nice to look at the effects of like a direct effect on the decompression rate, because this controls the melting during the later stages. But I haven't done it yet, so I'm not sure I can really provide any further information about this.
Other questions? Suzanne is first, and then Bonita. Oh, no, sorry, that was another one. Susan.
Hi, Pietro. I was just wondering a bit about your extension rates. You are 1 to 2 centimeters a year, so I guess you have some thermal cooling from above, right, while the extension is ongoing. So would your conclusions change if you would go to slightly higher rates as you proceed towards lithospheric breakup?
So the thermal boundary condition, you said there is cooling from above, but the upper thermal boundary conditions is constant, and
heat loss while you're rifting, right?
Yeah, okay, yes, there will be heat loss. Yes, I think if you increase the extension rates, that would be higher heat loss. And you would likely have an effect on partial melting as well, especially because crustal melting occurs to a large extent also because you are advecting hot asthenosphere at direct contact with the base of the crust. So if you increase the heat loss, that would diminish partial melting. So I would say yes, to some extent that would probably play a role.
I think because my guess is kind of that the dynamics in your system changes, right? Because if you extend faster, you advect the heat from the mantle faster. So you go to a different thermal regime.
Yeah. Well, in any case, even at slower rates, if you extend, given the set of conditions that I've been exploring, even if you extend at lower rates, you would break the mantle lithosphere relatively fast, and then you would advect the asthenosphere up to crustal levels quite fast. So I wonder whether the change in extensional velocity from 2 to 4 centimeters a year would condition significantly. I guess so to some extent, but I cannot really say to what extent.
No, I mean not either. I was just curious.
Yeah. No. It's certainly. But you do see an effect even in the range of parameters that I've been exploring. So if you switch from 1 to 2 here, then you produce overall more melting because you are advetting more. Also because you are advetting more asthenosphere faster towards the crust, but there is less effects from surface processes. Okay, so you would see more magma being produced, but less conditioned by surface processes.
Mm-hmm. Yeah, thanks a lot. I won't take more of your time now.